In the last part of surface preparation, we will discuss in detail the various surface treatments available. We are still in surface treatments or surface preparation. We know what are the general principles involved. Now we can describe in more detail the various surface treatments available regarding the passive treatments and the active treatments. That's what we will do in this module. So starting with the passive processes, and the simplest one, solvents. What do? Well, they clean the contaminants. They don't provide a very high strength. The most common solvents are those. Probably acetone is the most used one, and they can be applied in various ways: paper, spray, immersion, vapor. For example, in this slide you have the application of a solvent, acetone, using paper. Other passive processes, and this time mechanical ones, like shot blasting, or like emery paper, or like metallic brushes, that kind of things. What do? They remove also contaminants or rust, oxides. The manual processes like emery paper with your hand are more difficult to control, so shot blasting in general is the preferred treatment. It's faster and easier to control, and the particles that are used to shot blast vary. But we can have silica, silicon carbide, aluminum oxide, glass, etc. It depends also on the substrate. This. You have here an image of a shot blaster and pieces that are going to be treated with a gun and a projection of particles. The result is this. You have here in the slide, but I can also show you with a piece of aluminium the difference between the part that is shot blasted and the part that is not shot blasted. It's very clear. But if you make a zoom and observe this in the microscope, it's very clear the irregularities, which is excellent then to have mechanical interlocking. This contributes also to a good adhesion. Okay, that was the main ones concerning the passive processes, the one we use most, at least in the lab. Regarding the active processes, I will start with the chemical ones, and this is specially applied to metals and especially to aluminum. Aluminum is the material that is most studied in terms of surface treatment, and that's because it's the material used in the aeronautical industry. And as I told you at the beginning, the aeronautical industry is the pioneer in the use of this technology. So they have multiple recipes to treat aluminium. You can just apply an acid etching, or you can do it in a more controlled way using anodization. It's basically the same, but it's more controlled through an electric circuit. And at the end, the objective is to obtain this in a schematic term. This is the oxide. As you can see, a thick oxide, porous, and by capillarity, the adhesive can penetrate in these pores and create mechanical interlocking. So the oxide is very well defined, it's durable, it's resistant to corrosion, and very well bonded to the base material. This is a scheme, this is reality, this is the oxide, the porous one, the pores are here, and if you zoom less, you have something like this. So this is aluminium again. This part was anodized, this part is not anodized. It's very clear the difference between the two, all right? Okay, more processes, active processes. We have seen the chemical ones, now the physical ones. The physical ones are specially applied to polymers. I remind you, polymers by nature have a very low surface energy, and the objective is to change the chemistry so that the surface energy increases. You have here in this table a representation of groups that you can have and that will create secondary bonds, you know, the van der Waals bonds. Some of them are stronger than others, and we are looking for the polar ones. These in red are particularly low, very low. This one with fluor, this one is what you have with Teflon, very difficult to bond the Teflon. What we are looking for with the physical treatment is to obtain these groups that are very polar. But how do you obtain these groups? Well, all the physical treatments, and there are three mainly, you have corona discharge, you have flame, and you have plasma. But the three work basically with the same principles. What they do is that they will kind of burn the surface, they will break the molecules, and the molecules will react with oxygen. And they will create groups that are polar, and also this will increase the surface energy. Basically, that's what happens at the surface, all right? So, starting with the corona discharge, this is particularly adapted to film. So you have a film here, a polymer film. These kind of plastics are treated like this, polyethylene for example, and they go through a roller, this roller, and then you have an electrode, and this electrode will apply a chemical discharge at the surface that will kind of burn the surface, all right? Then you have the flame, like the name indicates, it's a flame, and you literally burn the surface. This is more practical to apply. You can transport the flame everywhere you want, and very applied in the industry. It's very easy to apply. And finally, you have the plasma. It's a bit more sophisticated. This time you use ionized gas. You bombard the surface with this gas. This will break the molecules, react to oxygen, increase surface energy, create polar groups, etc. It's always the same thing. Very nice to see before the plasma and after the plasma, the contact angle. Really, the contact angle decreases because the surface energy increases with the application of plasma. The plasma not only increases the surface energy, but also creates an irregular surface, which is good for mechanical interlocking. This is what you can observe at the surface. You can see it is irregular, but this is exactly what we want if we want to have, in addition to the adsorption, the theory of adsorption, the mechanical theory of adhesion. After we have our treatment, the question is, how long do I have to apply the adhesive? Well, it depends on the surface treatment, and many times what we do is we apply a primer, and the primer will protect the surface until I apply the adhesive. But primer can also mean adhesion promoter, which is exactly what is explained in this slide. In this part here, you just have secondary bonds, van der Waals forces, no electrons involved. In here, you apply an adhesion promoter, and then you will create chemical bonds, and this is way stronger than the physical bonds, but only if you apply this adhesion promoter. One of the most commonly used adhesion promoter is silane, and this silane will provoke chemical bonds between the adhesive and the substrate. But for you to have an idea of the time you have after you apply the surface treatment to apply the adhesive, solvent about 1-2 hours, shot blasting 4 hours, chemical treatment 6 days, anodization 30 days, And the physical treatments, coronary discharge, flame, plasma, you shouldn't take long after you apply that treatment. And that's it for the surface treatments. Now you have the most common ones and you know which one you can apply for a particular situation, for a particular substrate.